continuously streams real-time, high-definition video where we are the cast of the play that is taking place on Earth. It's a fascinating company. So, and after that, we will have a little coffee break, and I hope you'll all rejoin us for discussion, because there will be a lot of ideas, a lot of new things. We'll have some opportunity for a few questions at the end of each session, but there'll be so much fertile ground to discuss and really get forward that I hope you will all join me for the final session, which will take place at 4 o'clock. So that's basically the ground. I hope you'll stay with us, you'll enjoy, you'll participate, you'll be active. Without further ado, Bob, the floor is yours.
Good. Thank you. Well, good morning, everyone. Let me see if I can get my machine going here. Good. Yeah. Thank you, Max. You mentioned the company Silicon Graphics, which I had the great pleasure of spending 20 years of my life with, building the company and being its chairman and CEO. We did a few things that relate to this industry of geospatials. Number one, in the 1990s, we coined the phrase big data. That's become a very famous phrase now. At the time, we used it for several years, but the New York Times ran a discussion and a study of the etymology of the phrase big data, and they figured it out. It came from Silicon Graphics. Something else that came from Silicon Graphics was a company we pushed out of the door, which became a famous company called Google Earth. In the meantime, it was called Keynote, and Keyhole, sorry. Keyhole. And so that was also in the 1990s. But in fact, we did our business based on computer-driven visualization. And the idea was to tell the truth attractively. Bring up science, bring all that data out, make it visualized, and then engage the engineers, the scientists, the public, the policymakers, and in fact, try to integrate the opinions of all the different specialties on a visual rendering of deep science data. And geodata, geospatial data, of course, is a big part of that. So I'd like to now look a little bit, I retired from Silicon Graphics 8 years ago, and as a private individual, being very interested to create a Swiss Foundation with the purpose of continuing this work of visualizing difficult, large, intensive geospatial data, but in a dynamic manner such that it actually becomes storytelling. This is what I'd like to run you through. So we are collecting vast amounts of data. So we can model the surface, even the subsurface, the oceans, the atmosphere, even social economics, which is an overlay on the Earth. But it's time to actually stand out and attempt to model the whole Earth system as a holistic, integrated, very complex body. And that's the challenge I'd like to step up to. Of course, it's not an easy challenge. It's a very ambitious challenge, and it will take many years to achieve, and it will involve all the scientists and the scientific organizations globally. So we're definitely already in the era of what we call exascale, which means 10 to the power 18, that's a million. You can say bytes for storage, but it's also true floating point operations per second, flops, it's an exaflop era, it's an exabyte era, it's an exascale era. And we will go through this era in about a 10-year, 1 decade period of time. And then we'll be on to the next era, which is 10 to the power 21. And that's looking forward. 10 to the power 21 in our industry is zetaflop, zeta scale industry. And then 10 years later, we will be in what's called the 10 to the power 24 scale, which is the yotta scale. So we're heading in that direction. The good news is we can assimilate vast amounts of data today into modeling simulation, visualization, and that's how we comprehend the data. Otherwise, we can't comprehend such large volumes of data. The human mind cannot comprehend these large volumes unless we can model the data and put that data into a model. And the good news, and this is what I'm really an enthusiastic supporter of, the Joint Research Center in Ispra, Italy, together with the INSPIRE directive of the EU, together with GEO, and Barbara Ryan's team, and the Open Geospatial Consortium, they are all driving to get this data out to the public and available freely. So we need that. We can't go and collect that data again. It's just a formidable task to think about financing a recollection of all that data. So the old data and then the new data, the more it's freely available, the more we can use it for modeling, simulation, visualization, and understanding. So we have these tools. We have high-performance computing, cloud, the internet, mobile, and remote sensing. But now we're moving into what we would call real-time, predictive, big data, visual analytics. That's the era we're moving into with the tools. Of course, it's all software, it's statistics, it's algorithms, and applications, but it enables a new form of civic engagement through interactive visual narratives. And it's a new kind of storytelling. And this is the only way we will speak to, number one, the public, and number two, the policymakers of our society. This is the only way we will influence what we would call scientific-based, evidence-based decision-making. This is the name of the center which we have created here in Geneva, the International Center for Earth Simulation, a Swiss foundation. It's more than just a research program. It's about the insights into risk and predictability, public safety, policy guidance, and that includes like long-term food security, water security, energy security, of course. But it's a global thinking venture, and it's independent, not-for-profit, for public good, and philanthropically funded. So this is the only way to get above all the machinations that take place between the governments and industry and finance. You've got to get above all that if you want to deliver this independently minded, neutral platform. Well, of course, the world is complex. Truly, truly complex, massively complex. And in addition, it's all connected. Everything is connected. Everything is teleconnected, telecoupled. That means over distance, not necessarily cheek to jowl, but you've got thousands of kilometer effects and oscillations across the entire planet. In fact, the truth is the whole solar system is dynamically interconnected, and our sun is the driver. So we can't really model the Earth until we start to model the sun and know how the sun is performing. And it's performing with an 11-year sunspot cycle, which is quite variable. And here is some real data. This is the sun ejecting what's called a corona mass ejection over an 8-day period in March of last year. And this is the Earth being impacted by the coronal mass ejection. Here, the inner planets are Mercury and Venus, and then outside of us, we have Mars and Jupiter. But you can see we're flying around. Our Earth spaceship is flying around in a very toxic environment. And there's a tremendous amount of space weather between the sun and the Earth. And we actually haven't come to grips with this space weather yet. I mean, switch the television on in the morning and you can always watch regular weather. But it won't be long before the broadcasters will be speaking about the space weather forecast between sun and Earth. Fortunately, we have a shield. The magnetosphere of the planet shields us from that toxic environment. And it's a multi-layered shield. It's not a simple shield. This shield has a complex electronic structure to it, electromagnetic structure. A lot of current is flowing through it, this shield. And inside of that shield, there are 3 additional shields known as the Van Allen belts. And we've recently been putting up satellites that look at this magnetosphere, the shield, and the Van Allen belts. So we've got our eye on it. The satellites, the new satellites, are all looking at this on a 24-hour basis. So we're starting to understand it more. Underneath the Van Allen belts, we have the ionosphere, which is closer to the Earth. And in fact, that has a complex structure too. It has a DEF layer. But we have a lot of bleeding of electronic current down from the magnetosphere to the Van Allen belts to the ionosphere, and then ultimately to the Earth itself. And that's known as the global electric current. And it's driven by hundreds of thousands of volts. And when it goes wrong, when we get some kind of extraordinary leakage, we'll see our grid structure, electric grids, knocked down, which they are often. And we'll see all our satellites go dead. We'll see the GPS systems lost. And can you imagine how much havoc these so-called geomagnetic storms will create? And they do create. The most famous event is called the Carrington event, which was actually 1859. And of course, since that time, we've developed a much more intense grid structure, electric structure for the planet since then. So we're much more vulnerable now than we were at that time. Now, of course, we know the ocean climate system. It's driven, an ocean wind coupling drives most of our daily climate. And the convection of clouds is still somewhat of a puzzle. We haven't fully understood this to model this yet. But again, it's the latest leading edge area of focus. Morning, Tom. We can model pretty well today the atmosphere. That's the good news. We are able to bring all that data together, model and simulate the cloud formations, the wind formations, cyclone genesis, the formation of cyclones. We're pretty much on top of that today. That's the good news. Things have come that far. But inside of that system, there are components. There's the carbon cycle, the nitrogen cycle, the phosphorus cycle, the sulfur cycle, and even the water cycle. The full complexity of these global cycles is not yet understood. So we're missing these particular components. We're striving to get the geospatial data to understand these cycles. That's really one of the frontiers. And when we add these cycles, when we get the knowledge of these cycles into the models, combined with the atmospheric models that we have, will be a big step forward in understanding the planet. Now, we may think that we've got some things figured out, like, you take wind turbines. They're a good alternative energy source. And you can just take energy from the wind. But it's not a freebie. See, everything is interconnected. If you take energy from the wind, you do change the climate on the other side, downstream. This is a perfect example. This is a picture from Denmark. And the thing is so fragile, our system is so fragile, that if you do take energy from one part of the system, you will affect another part of the system. This is the complexity, the interconnection, the telecoupling of everything. And this is a perfect example of how the climate downstream from the wind turbines can be changed. That's a perfect example. The other coupling factor of this planet is aerosols. So the winds pick up aerosols and transfer them all around the planet. And here you can see this is the Sahara being coupled in, transferring dust and other debris over to Central America and Latin America, including the Amazon. This gray band here is the industrial pollution, sweeping across the northern hemisphere between North America, Europe, and Asia. Down here, this blue band of transfer is sea salt spray, much more innocent. But you can see the intensive coupling that's taking place all around the planet all the time. And again, it's part of our modeling simulation and visualization effort to track that data. And this is geospatial data. Now, what about the ocean? We had a good talk yesterday about the ocean. What we didn't touch on is the conveyor belt. There is a massive conveyor belt that connects all the oceans of this planet. Since the oceans occupy 70% of the planet, and they are connected by the conveyor belt, you would think this would be the major element driving our climate. And you would be right, it is. What can we say about it? Well, if we model and simulate this conveyor belt, this is what it looks like. Coming up here, alongside of South America, and then North America is the current, heading towards Europe, getting colder, losing heat, and then falling to the bottom of the seafloor. And then turning, and then coming back southward. So I think we will understand North Europe is probably 5 degrees centigrade warmer than it would otherwise be if this current didn't exist. But that cold water is now flowing back south underneath the warm current, heading back towards the Southern Ocean. And the Southern Ocean is the powerhouse of the planet. It's a circumpolar ocean that circulates continuously around Antarctica, the continent. This is a massive ocean, and this water flows on underneath the Indian Ocean and then loops back up in a similar manner in the Indian Ocean. So now the Atlantic Ocean, Indian Ocean are coupled, the water comes back under Australia and does the same thing in the Pacific. But let me stop that here. I stop it because that's my hometown right there. And I'm sorry, home, sweet home. And I have to show you a picture. That's my own camera looking south from a town called Encounter Bay, which is a famous meeting location of a French explorer, Nicolas Boudin, and an English explorer, Matthews Flinders, that met by accident at this bay, which is by my hometown, looking south towards the Antarctic. But that's not the end of the story. This planet of ours, we're living on a living planet. Our planet has the crustal plates, tectonic plates, and they're all moving around, bouncing around. Some of them are grinding and some are passing underneath the other. And this continuous grinding and bouncing is causing us to have daily earthquakes all over the planet, some of which are highly dangerous. As you know, when one plate goes under another, the friction is so great, it's called subduction, but nearby to that heat, you'll see a line of volcanoes pop up. And these volcanoes are changing our climate and interfering with our climate because, for example, in the Pacific Ocean, we have the famous Ring of Fire. Around this ring, where the plates are actually subducting, we actually have over 400 major volcanoes. And as you know, there are always, somewhat unpredictably, outgassing enormous amounts of material, carbon dioxide, sulfate, etc. Every volcano is different. This happens to be a picture from Iceland, and we all know how that stopped our air traffic here in Europe in 2010 for about 8 weeks. So this interior of our planet is a big challenge for geospatial data. Geospatial does not mean geospatial surface data only. We've got to get to this, understanding the complexity of the inner Earth. And the inner Earth, as far as we know now, is highly plastic and highly dynamic and has a lot of convection currents inside it. So we're still learning about this inner Earth with new instrumentation, but we do know that this magnetic dipole that's been set up here and creates the magnetosphere that I mentioned earlier, it flips from time to time. So can we predict when it's going to flip? No. Do other planets have it? Yes. Does it flip in other planets? Yes, it does. So this is a phenomenon that we've got to come to grips with. When it flips, we'll definitely see a major disruption in all of our technologies. Let's move on from the natural system to our overlay social economic systems. But there's a coupling. You shouldn't think that they're independent. They have now become highly coupled and interwoven. Our natural systems and our social systems. So here, we have the phenomena of sequential collapse, synchronous collapse, and multiple synchronous collapse, cascading across the boundary between natural and social systems. And this, of course, involves everyone on the planet. It impacts everyone on the planet, and it can be highly disruptive and lethal. This is just, in the last 10 years, the kind of events that point to the coupling and the danger of the coupling. Whether it's the Southeast Asian smoke haze, European heat wave of 2003, I've just highlighted the European ones, the English floods, the Icelandic ash cloud, the Russian heat wave, more recently the North German floods. But you know, we are in for, the planet is in for just a high frequency of these major events that cascade between nature and society. And this is where geospatial data is a tool to help us predict, understand, and even take action that would help us avoid the danger of those events. The big one, the big daddy of them all, most recently, of course, is March 11, 2011, the Great East Japan earthquake. This is a scientific rendering of the horizontal displacement. Japan moved permanently 5 meters to the east, permanently. That's the scale of these measurements. These are all GPS measurements. It pulled Korea and China with it to a lesser extent. In fact, if you look at the scale of the red arrows, it's about 3.5 centimeters. So the whole of China moves 3.5 centimeters. In fact, if I were to show you a different picture, the Tibetan Plateau is rotating clockwise, and then Australia and India are moving up northwards at about 4 centimeters a year. So this is a dynamic planet we're on. So if we think we're pinning down geospatial data and that's it, no. We have to keep doing this. This planet is moving. This planet is dynamic. So if you look at this cascading synchronous collapse in the case of Japan, you had a 9.0 earthquake, you had a 10-meter tsunami, 400,000 structures destroyed, all the manufacturing supply chains disrupted around the world, 3 nuclear reactors down, the world's largest utility goes bankrupt, Prime Minister forced to resign, Switzerland, Germany decommit from their nuclear strategy, and global nuclear industry changed worldwide. Now, what else is there? It's not over yet. Because here we have now a slow bioaccumulation of nuclear contamination in the North Pacific Gaia. And you have all the salmon runs here in North America that their fish go out into the sky and spend 4 years here before they come back. They're coming back this year. And this is a great fear of the danger and what level of bioaccumulation of nuclear materials is collecting in the wildlife and the biota of the North Pacific. So here's the question. If you look at this rendering, we have a lot of planetary boundaries that we're starting to get close to, danger points. If we can pull back from these boundaries into a safe zone, we will ensure our survival. But if we go over, there are points of no return where we can't get back. And if we have enough parameters that go over into the danger area, we will be in this zone of what we call the 6th extinction event. The planet has had 5 of them already in its history. And the question is, how far are we from a 6th? And the thought is, there are enough boundaries now that we can recognize, critical points, thresholds in the planet, that if we drive enough of these points into the danger area, we'll finish here in a sixth extinction event. Of course, no one wants to be there, but I think a question of education and discussion across the whole of society, using a vast amount of geospatial data and applications and visualization and discussion and civic engagement to bring these conversations to a head, and such that our global policies are more evidence-based than they were in the past. Now take a look at this. This is the big picture. This is the last thing I'm going to show. Visualization at its best. This is a simple example of the moon circulating the Earth, circulating the sun. Now if I put a vapor trail, you can see a little more what that looks like. And if I show you a backdrop of some of the stars, this is how dynamic our system is. The moon circulating the Earth, circulating the sun, and now I'm putting here the calendar, because it's all synchronized seasonally with a calendar. So this is a perspective of who we are in the universe. This is our cosmology. And it's not as simple as this either, because in fact it's all wobbling. You know, the orbits are not perfectly circular, they're elliptical. The axis of the ellipse is precessing as well. So I'm not going to show that, it's too much fine detail. But here's a big perspective of this planet of ours in our solar system circulating around the sun. Now, in fact, I can marry and synchronize this calendar with the seasons. So the seasons of the Earth, the breathing, the respiration of the planet is synchronized, of course, with the calendar and with the seasons. And this is a perfect example of how you can look at both at the same time. It's geospatial data used in a storytelling manner, but tell the truth attractively. You've got to have the scientific data underneath this. You don't want to present the public data, which is not correct. Or if it's speculative, you have to say it's speculative, and so people understand what they're seeing. But it's a perfect juxtaposition of the breathing of the planet and its solar orbit. But we don't have to finish there. We can take visualization several steps further. And again, I think for good reason, because our solar system is in a Milky Way galaxy. And we are rotating, in fact, around that galaxy. Here's the Milky Way galaxy. This is speculative now. We don't have all this data. It's moving, the galaxy itself is moving. But here's our solar system rotating inside the Milky Way galaxy. It has a 300 million year orbit time to go around the entire Milky Way galaxy. And it undulates up and down. And here's the tree of life on our planet, emerging with all of its species with this particular calendar. And here's the continents being formed, again synchronized. So if you see this data, it's publicly available data. It's speculative data, by the way, but you can see we ultimately get the map that we know. We ultimately have this very complex tree of life, and we see that our solar system is rotating in the Milky Way galaxy. And hello, this is man evolving out of Africa and migrating across the planet. Again, it's speculative. We don't have all the data. We think it looks like this, but we could argue the details night and day. But again, it's helpful to know how man inhabited the planet. And I could go a little bit beyond this too, with final, and it's a very interesting population growth chart, visualization. Here's our migration path, but what was the population build-up? This is since AD 0, and here we go. Every pixel is a million people here in this chart. And we watch the population of the planet grow, and then finally, after the Industrial Revolution, we watched the population of the planet explode. That was 1750, it was the Industrial Revolution, which spread around the world, made us a little bit more durable, and as a consequence, well, scary. So I'm gonna leave it at that, and I say, well, you know, this is what the big picture looks like. This is what geospatial data looks like. This is how it can be used. I think it will be used in this manner. And I'd like to say that the ISIS Foundation is aimed at using the data in this manner, in that way for public good.
Thank you very much.
Great, thanks.
Well, I promised you inspiration galore, so yeah. The man has a vision.